Hey folks, my name is Nathan Johnston. Welcome to Lecture 10 of Vector Calculus, which is all about scalar line integrals again. We already had one lecture video about scalar line integrals, but in that previous lecture video, we talked about, how do we come up with a formula for computing this thing, and what is it that we're trying to compute in the first place? Like, what is the scalar line integral? Now, today, we're going to make use of this formula that we came up with, go through a bunch of examples, and talk about a couple other ways of interpreting it, okay? So let's start off with an example where we just literally compute the thing, okay? Devoid of any context. It doesn't necessarily have any nice physical meaning or anything like that. It's just compute the scalar line integral, okay? So compute this scalar line integral, okay? So first off, what this notation means, it means I'm integrating along a curve, because that's what a scalar line integral is, and the scalar function I'm integrating is this thing here, this x times y. Okay, so that's my scalar field. It's x times y. And what is the curve? Well, it's the intersection of two surfaces in three-dimensional space. The first surface is defined by this equation here, x squared plus y squared equals 1. And I've claimed that's a cylinder. So why that's a cylinder is, well, okay, in R2, like if there was no third variable z here, if it was just in R2, x's and y's, this equation would be the equation of a circle of radius 1, right? Okay, and now, like, okay, if it's in R3 though, like, how do I interpret this? Well, it's just the value of z is irrelevant because it doesn't show up in that equation there, okay? In other words, if it's true for some particular xyz pair, then it's true for every xy pair that has the same x and y. Like, the z's irrelevant. So, like, if it's, includes the circle on the floor, it includes every circle of the same radius, no matter how it's shifted up or down. Okay, so this is a cylinder radius 1 centered around, the z-axis. Okay, and then this is just some plane in three-dimensional space. And the question is, okay, integrate along the intersection of those. The intersection is going to be sort of a slanted circle or something like that. Integrate along that slanted circle to compute this scalar line integral. All right, so how do we do that? Well, we just got to plug into this formula that we came up with last lecture. And so we need to know what our x, our path is, and what our f, our scalar field is. So let's start off with the scalar field. What's our scalar field? Well, it's the thing you're integrating, x times y. Just be a little bit careful. It is a function of three variables here because everything here is living in three-dimensional space for this particular example. Okay, so even though there are no z's over here, it is a function of x, y, and z. All right, great. So I've got half of it. I've figured out my f. What's my path? What's my x of t? Okay, and for that, I've got to figure out some way to parameterize the intersection of these two surfaces. And the trick here, what I'm going to do is I'm going to say, okay, x squared plus y squared equals 1, that looks a heck of a lot like a circle. And in particular, if I say, okay, my x coordinate is cos of t, my y coordinate is sine of t, then I know every point on my path is going to be on, this surface at least. Okay, so if I choose my x and y coordinates in that way, it sort of takes care of this piece. And now I've just got to pick my z coordinate so that it's also satisfying this constraint over here that x plus z equals 2. And to do that, I just say, okay, well, what's my x coordinate? Oh yeah, I chose x to be cos of t. So if I just choose my z coordinate to be 2 minus cos of t, then this constraint over here is satisfied, okay? And I mean, sort of like the way to think of this is here I've got a two-dimensional surface, intersect them, I get a one-dimensional curve, which is parameterized by this path now, okay? All right, and I'm just going to take t going from 0 to 2 pi, just so that I only go around the cylinder once. So I only go around the slanted circle that is the intersection of those two surfaces only once, okay? And now, well, I mean, I want to integrate next, maybe just a little bit before I do that. My formula for the scalar line integral, it has this piece over here where I need to know the speed of the path. So let's compute the speed of the path. And the way that you do that is, remember, take the derivative of each entry. So cos becomes negative sine, sine becomes cos, and 2 minus cos becomes sine. And then compute the length of that vector, okay? The length of this velocity vector. You just square each entry, add them up, square root the whole thing. After I use the fact that cos squared plus sine squared equals 1, it simplifies down like this, okay? The speed of the path is the square root of 1 plus sine squared. Okay, and now I can just plug everything into my scalar line integral formula. And when I do that, what do I get? Okay, so notation for scalar line integral, formula for scalar line integral, and now I start plopping all this stuff in. Okay, so f of x of t. Well, f of xyz is x times y. So what I do is I just take the x component of x of t and multiply it by the y component of x of t. Okay, in other words, I take cos and multiply by sine. Okay, that's what f of vector x of t is. So this cos times sine, that right there is f of x of t. Okay, and then I also need the speed of the path, which we just computed. It's the square root of 1 plus sine squared t. Okay, and that's the integral that I compute, and I integrate across the time domain. Okay, so the bounds on the integral are the bounds on wherever t is allowed to go from. Okay, and now I just compute that thing. Okay, it's a little bit of a messy integral. Okay, maybe it takes you a little bit to remember how do you do things like this. Okay, this particular integral, the thing to note is that this stuff on the outside, this cos times sine, is up to scalar multiples, just the derivative of this stuff on the inside, right? If I do the derivative of sine squared, I'm going to get 2 times sine, and then chain rule kicks in, and I get times a cos as well. So this thing in here is just 1/2 of the derivative of this thing over here. Okay, so you can integrate it just, I mean, depending on how comfortable you are with this, maybe you can just do that in one line. Maybe you need to explicitly write out, like, basically this is an integration by substitution, sometimes called a u substitution, where you say, okay, u is the stuff in here, and basically du is the stuff out here. Anyway, after you do the integral, you're going to get this junk here. And now we just got to plug in the endpoints of our integration. When you plug in 2 pi, you just get the 1/3 here. The sine squared of 2 pi is 0. And then minus, plugging in 0, well, also 0 here. So you're just going to get 1/3 minus 1/3. So the integral as a whole is just 0, okay? The value of that scalar line integral is 0. And sort of the way to think about this, like, why is it 0? What's happening here is, well, geometrically, again, like, sort of the curve that we're integrating across is sort of this slanted circle here. Okay, and what's happening is the values of the scalar field are sort of equally distributed across plus minus values along that slanted circle. Okay, the z value doesn't matter in the scalar field, and along this circle, there's like for every value, every positive value of the scalar field. Well, if you just sort of go across that slanted circle, you're going to find the exactly equal but negative value of that scalar field as well. So they're just sort of perfectly balanced around the scalar circle. Across the scalar field, and you end up getting 0 as your integral for that reason. Okay, so let's talk about some other ways of sort of interpreting or thinking about scalar line integrals, okay? And sort of one of the most common ways of thinking about it is, okay, recall that a scalar line integral, the point of it is it's what you get when you sort of accumulate a scalar field along a curve. Okay, well, if that scalar field represents a rate of something, then accumulating it just gives you sort of the non-rated version of that, if that makes any sense. Okay, so like for example, if the scalar field tells you the density of something, right, like the mass per unit of distance of something, then integrating it is just going to tell you the total mass of that object. Okay, so let's do an example with that sort of in mind. Okay, so let's talk about like a wire that's in space, and what we're going to do is we're going to integrate along that wire. We're going to integrate a density function, and that'll tell us how heavy the wire is. Okay, so suppose that we've got a wire parameterized by some path. Okay, here t is going from 1/2 to 2. Okay, the wire is living in 2-dimensional space. And everything here, all distances are measured in meters, okay? If the wire has density 18x minus y squared, measured in grams per meter, what is the total mass of the wire? Okay, so again, like the reason this is going to work is because the scalar field, this 18x minus y squared, that's our scalar field, our f of xy, that's a sort of a rate of something, right? It's grams per meter, okay? If you've got sort of a quantity per unit of distance, then integrating this with respect to distance, which is what a scalar line integral does, is just going to give you, the mass, the grams. All right, so let's do this, okay? How do we do this? We're going to need to figure out what our scalar field is. Well, we already did, okay? It's this 18x minus y squared. We also need to figure out what our path is, and oh, beautiful, that was given to us in the question. Okay, we were given a parameterization this time. So now we just plug everything into the formula, right? We're going to need the speed, which first requires us to take the velocity or the derivative. So just take the derivative of each entry, and you get this junk here. Compute the length of that vector, okay? So first entry, squared. Second entry, squared. Add them up, square root the whole thing. That's the speed of our path. And it's just some ugly mess, but it is what it is. Next up, integral, okay? Scalar line integral equals formula for scalar line integral, and just plug everything in, okay? This speed component over here, that's just this formula. F of x of t, well, what you do is you go to your f of xy, and you plug the x coordinate and the y coordinate of your path into it, okay? So instead of 18x minus y squared, now it's 18t cubed minus, well, not y squared, 2e to the minus t squared, okay? So 18t t cubed minus 2e to the negative t squared. This is 18x minus y squared, just with particular x and y coordinates plugged in. Okay, and then this part over here, this is the speed. Okay, and again, you're just integrating, over the time domain. Okay, t was going from 1/2 to 2. That was the domain of our path, so that's where you're integrating. Okay, and something very similar happens in this example as to what happened in the previous example. It turns out this stuff out in front here is basically just the derivative of this stuff on the inside. This, I should clarify, this does not always happen with scalar line integrals. It just happened to happen with these two examples that we've gone through here. The next example is going to show something different happen. Okay, but again, so you can do this integral via u substitution. You just say, okay, the stuff on the inside of the square root, that's my u. And then my du is the derivative of this dt, okay, which you'll notice that's just double this stuff over here. Okay, so that lets you compute the integral chain rule in reverse or integration by substitution. However you like to do it, either way, you end up getting 1/3 9t to the power 4 plus 4e to the negative 2t, all to the power 3/2. And now you just plug in your endpoints, okay? When I plug in 2 for t everywhere, I just get this ugly mess over here. When I plug in 1/2 for t everywhere, I get this ugly mess over here. I just subtract them, and it's some number. I mean, you could probably simplify and clean that up a little bit, but whatever. That's the exact answer. If you want sort of a more numeric answer that you can actually sort of think about, I mean, plug that into a calculator and plug that into a calculator and you get something like 575.47 grams. Okay, so that's how heavy the wire is if its mass is distributed in this way. And if you sort of look at this plot here, like what's happening is you've got this wire. It's not super duper bendy. It's more bendy on the left than on the right. But on the left, the wire really doesn't have much mass, okay? Like it's much lighter on the left, whereas the values of the scalar field on the right side of the wire are much higher, so it's much heavier over there. And the scalar line integral is how you sort of add up all those different contributions to get the total mass, okay? Alrighty, one thing worth noting here is, okay, what if instead of the wire having this weird density function that makes it heavier in some spots and lighter in other spots, what if its density was uniform? And even more specifically, what if its density was just 1 gram per meter everywhere? Okay, so every meter that you walked along this wire, you just picked up 1 gram, okay? What would the scalar line integral give you in that case? Well, okay, we just talked about, like, of course, it's got to give you mass, just like it did up above. The only thing that's different is what the density is. The interpretation of the scalar line integral is still the same. So it's still going to give you mass, except if this is your density function, like if every gram corresponds to just a meter, then the mass is going to equal the length, right? The number of grams equals the number of meters. Okay, so what would happen is this integral, it would also give you the length of the wire. Which, fortunately, this makes sense, actually. If you run the math here, okay, if your scalar field is 1, right, if your density function is 1, then f of x of t is always equal to 1. And then if you plug that into our scalar line integral formula, then yeah, scalar line integral equals formula equals, well, this first chunk here, that just equals 1, so it goes away. And you're just left with the integral of the speed, which, remember, we know what that is. The integral of the speed, that's our formula for the length of a curve, okay? So the scalar line integral is just the length if your scalar field equals 1, okay? Alrighty, one final way of interpreting scalar line integrals is you can think of them as two-dimensional areas in three-dimensional space, okay? So in other words, if your scalar field, now we're not thinking of it as like a density or anything like that anymore. This time we're going to go back to our earlier way of thinking of scalar fields or multivariable functions as like a height, okay? We're going to think of them as their graph, right? If we have a multivariable function, a scalar field, then I can think of that as like a surface in n+1 dimensions over n-dimensional space. Okay, and now what a scalar line integral is it's what you get if you have a curve under that surface and you want to know, hey, what's the area above the curve but below the surface? Okay, so for example, if we go back to this example that we just went through, okay, we had this wire, this curve or this path, okay, and we had a scalar field, okay? If instead we reinterpret the scalar field's not density anymore. Now this 18x minus y squared, I'm going to think of that as height, okay? It's elevation. Okay, so like what happens now is I get a surface over two-dimensional space. That's what this red surface is. That's the 18x minus y squared. It's a surface in three-dimensional space. Okay, and what I'm doing, like this previous integral that we just computed, this 575 grams, I could also think of that as the area of this blue region. This blue region, it's two-dimensional, okay, and it's just like I took a sheet of paper and I bent it to the shape of the wire, and then I cut it off at the height 18x minus y squared. The area of that sheet of paper is also the scalar line integral that we computed. Okay, so let's do one more example with sort of this interpretation in mind. Let's compute the area of a 2D region in three-dimensional space. That's what these scalar line integrals get for you if you're interpreting in this way. Under the surface, z equals 2 minus x squared plus y squared, but above the circle, x squared plus y squared equals 1. And by that, I mean like the circle in like the floor, in the xy plane. Okay, so we need to figure out what our scalar field is, and we need to figure out what our path is. And the scalar field, remember, that's the surface, okay? That's like, I'm thinking of it as like a surface graph of a scalar field, okay? So that's my f of xy, okay? What's the path? Well, I mean, above, that's the thing that you're going above. That's the curve that you're integrating above. So that's the circle in this case. So I'm just going to parameterize it in the usual way, cos t sine t, and t going from 0 to 2 pi, because I just want to go around the circle once. Okay, I'm going to need the speed of this path to compute my scalar line integral, and the speed of this path, I mean, it's this is like our arc length parameterization of the circle, right? If you compute the length of the velocity vector, you're just going to get 1 because sine squared plus cos squared equals 1. Okay, so the speed of this path is everywhere 1. So now we're able to plug into our scalar line integral formula, and the area, this two-dimensional area, it's scalar line integral, which, okay, here's the formula for it. The endpoints are just my, domain endpoints. I just plug everything in, okay? This speed here equals 1, so this term here, it's just going to go away. I've just got f of x of t, and what's that? Okay, well, f is this, 2 minus x squared plus y squared. Everywhere I see an x, I replace it by cos, the x-coordinate of my path. Everywhere I see a y, I replace it by sine, the y-coordinate of my path. So I'm going to get the integral of 2 minus x squared plus sine squared. Okay, and I've got to compute this integral. I don't like integrating squares of trig functions, right? So use some trig identities. In particular, you can recall this one, cos squared minus sine squared equals cos 2t. Okay, and then you can replace all this stuff over here by negative cos 2t. And that's a lot easier to integrate, right? Because, I mean, now it's just a little chain rule. You're going to get an extra 1/2 out in front when you integrate that. But otherwise, cos just turns into sine. And now you plug in your endpoints, plug in t equals 0, plug in t equals 2 pi, and when you do that, you're going to get 4 pi as your final answer, okay? And what that tells me, so here's the plot of what we just did, okay? So that red curve up top, that's the surface. That's the z equals 2 minus x squared plus y squared. Okay, and what we computed, though, was the area of that blue truncated cylinder down below it, okay? That blue area that's above the circle, but below the red surface, okay? So the area of that region is 4 times pi. That's what the scalar line integral gave us, okay? And that'll do it for scalar line integrals. So thanks for watching, everyone. I'll be back in a few more days when we start talking about vector fields and vector line integrals. So I'll see you then.